Okay, that's enough for SRAMs for now. Next, we'll be going into serial access memories. And these serial access memories don't use an address and so don't need the decoder logic that we were talking about with SRAMs. Some examples of serial access memories that we'll be going into are shift registers, tapped delay lines, serial input parallel output, which is called SIPO or SIPO, parallel input serial output, which is PISO, and queues, FIFO and LIFO, which are first in, first out, or last in, first out. And we'll be going into each one of those in the next set of foils. So shift register is one type of storing of values. Shift registers both store values and they also delay your data. So if you don't want to use the data immediately but you want to delay it for a few stages, you can use a shift register. So below is a simple design shown for a shift register where you just have a cascade of registers. You have like, let's say, a set of flops. In this case we have 4 flops, and here we're showing the hash line with the number 8 there means you have 8 flops in parallel, and you have an 8-bit value coming in, and then you have 4 sets of those in series with each other. So you just have the output of the first set of 8 comes in from a data value 8 wide bus, and it goes into a next set of 8 in an 8 wide bus, and so it takes 4 cycles for D in to get to D out, and in this particular case it just shifts through, and 4 cycles later D in comes out at D out, and in the meantime it's just storing 8 bits wide. It's storing 4 values in series before it goes from in to out. Now, an extension of a shift register is using a tapped delay line. So as I said, with a shift register, you not only are storing value, but you're also delaying the value, the time between when data comes in and when data goes out. Let's say you want to program the amount of time that it takes for the delay. In the previous example, we only had a delay of 4 because there was exactly 4 registers in series with each other. Down below, you can see here an example of how you could have a programmable delay from 0 to 63 stages worth of delay. And the way that this is done is we have a variable, we have a set of shift registers that are between 1 register up to 32 registers by factors of 2. So we have a shift register that's 1 long, a shift register that's 2 long, shift register that's 4 long, 8 long, 16 long, and 32 long. Then we use muxes in between the shift registers to decide, do we allow the data to bypass a given shift register, or does it need to go all the way through that shift register? So if we have, for example, if we allow delay 5, 4, 3, 2, and 1 to all choose the value of D in that goes around the shift register as the value that goes through the mux, then when D in comes in, it goes through the mux delay 5, through the mux delay 4, delay 3, delay 2, delay 1, and then let's say the delay 0 mux chooses the output of the shift register to go through that mux. So we go through all of the bypass paths, we go through and get captured in shift register 1, shift through in 1 cycle, and then go to D out. If, on the other hand, we wanted to delay by 5 cycles, we would bypass shift register 32, 16, 8, and then we would force it to go through shift register 4, and in delay 2 mux, it would choose the output of shift register 4 to go through the mux, bypass shift register 2, go through delay mux 1, and then delay 0 would choose the output of shift register 1. And so if we wanted a delay of 5, we'd go through shift register 4, shift register 1. We'd have a total delay of 5 cycles to go to D out. And of course, we can program, depending on how we program the 5 or the 6 different muxes, we can get anywhere from 1 cycle or 0 cycles of delay to 63 cycles worth of delay. So make sure you understand that. Should be a relatively simple concept, but if you want to go through it, pause here and you can go through it in more detail. So here we have the concept of a serial in, parallel out. So we're using this is just showing a single bit. So a 1-bit shift register that is a 4-bit input serial in. So we take 4 cycles to read in the serial data. And so 1 cycle at a time, we're reading in 4 separate cycles worth of data. And then once we get 4 cycles read in, then a different output logic will take the values of P0, P1, P2, and P3 to read all 4 of those in parallel with each other to go to some other logic. And so we're reading in a single bit serially for 4 cycles, and then once it's been read in, we take that logic and take all 4 bits at the same time and use them in parallel. So the number of steps is the number of parallel bits that we're taking at the output. So the previous foil went through serial in, parallel out, or SIPO. This foil is the flip of that, where we have parallel data coming in and we're reading it serial going out. So the flipped version, like we had in the last foil, we had 4 bits. So here we're loading all 4 bits at the same time into the 4 registers, and then we're shifting out 1 per cycle. And so in this case, we actually need a 2-to-1 mux going into each of the memory elements, because we need to know whether we're loading the values in parallel or whether we're shifting them out. So when we're loading them, we choose the top input to the 2-to-1 mux, and we then of course need a controller for each of the 2-to-1 muxes that's controlling whether we're doing the shift or whether we're doing the load. So when we're high, we're choosing to do the shift, and when the value of the select is low, we're choosing to do the value of the load. And so again, this is just an example. There's probably other ways you could do it as well, but this is one simple example. So queues are another type of memory array that we can use. Queues allow us to data to be read and written at different rates. And so you could have 2 different clock frequencies being used, or it could just be that maybe you might be able to read at different times than than the values were being written in. You might have a burst write, for example, and you can only consume the values from the write at a different rate. And so you might write in like 20 values and then you read them out over time. and you know that the writes come in at a burst, and so as long as you can read them out over a period of time and then you get another burst come in, you know over time you average out and you're okay, but you might need to store the values so that you have time to consume them to do whatever calculations you need to do with them. So as I said, the read and write each use their own clock, and they each pull the or read or write the data at their own time. So in addition, the queue has to indicate whether if it gets full. So if you're trying to write data in, whatever's doing the writing has to know that the queue isn't totally full. And so there's a signal that says, hey, my queue is full, you can't write any more data in, and you have to pause doing whatever you're doing. In addition, whatever's reading out of the queue has to know whether there's data in there or whether it's empty. It doesn't necessarily on either side need to know how full or how empty. It just needs to know when you're writing, once it gets completely full, you can't write any more values, and if you're trying to read, once you're completely empty, you can't read any more values. So those are a minimum of the types of control signals that you need for a queue. And you could wind up building a queue using a SRAM, for example, and then you just create read and write counters and pointers as part of your additional logic around the SRAM. There's obviously other types of, you could build it as well with just an array of flip-flops, for example. It just might not be quite as dense as an SRAM would be. Two specific types of queues that are typically used are FIFO and LIFO queues. A FIFO queue stands for first in, first out, and that means that whatever values go into the queue, the earliest value that goes in is going to be the earliest value that goes out. They go out in the same order they went in. So you initialize your read and write pointers to the first element, and you just go in sequence as they get written in, you go in sequence, and as they get read out, you go in sequence. And you read it out until the queue is empty. As you're doing your write, you increment your write pointer, and as you're if the write catches the read, so as you're writing, you increment your write pointer. As you're reading, you increment your read pointer. And if your write wraps around and catches the read, and they become the same value, then you know the queue is full. And so you indicate that to the write full value. The other type of queue that is typically used is last in, first out. This is also called the stack. So as you put a value in, whatever the last value that was written in is the next value that gets read out. So it's as if you were stacking things on top of each other. So if you stacked papers on a desk, the last paper you put on top is the first paper you take back off the top. In this case, you can use a single pointer for both the read and the write. It's just the stack pointer saying how tall is the stack. If you get all the way to the top of the stack, then you're full. As far as writes go, you're full. If you get all the way to the bottom of the stack and you get down to 0, that means you can't read any values, and your read pointer is reading empty. So two different types of queues that are commonly used.